Hello, welcome. This video is to teach you what is meant by standard electrode potential and how can we measure the standard electrode potential. By making use of the standard electrode potential, then definitely we can know what is the potential difference between two metals. By using this, then we can start to create our own battery. So, what is meant by standard electrode potential? Standard electrode potential means a metal is placed in its respective ions with a concentration of 1 molar at 298 degree Kelvin or 25 degrees Celsius. So the potential obtained when it is compared with the standard reference, then this potential is what we call the standard electrode potential. So say for example, if I want to know the standard electrode potential of iron, then I have to prepare a piece of iron metal and then immerse it into a beaker of solution of iron 2 sulfates. So this is how we prepare the half cell of the iron standard electrode potential with 1 molar and 298 K. So this is the half cell that we have to prepare. But what are we going to compare? If I have only iron, then what I have to compare? What is the standard, or what is the thing that I should keep it as a reference? So we should use the simplest atom that we have in the world, which is hydrogen. So we try to use hydrogen as a reference. So let's look at this cell. The cell here contains a chamber that we can input hydrogen gas at 298 K, and then we pump in hydrogen gas at 1 atm, and then inside this hydrogen half cell we've got a platinum electrode. This whole setup will immerse into a beaker of hydrogen ion at 1 molar. So what is meant by this solution containing hydrogen ion at 1 molar? We all know that hydrogen ion always comes from acid, so we can always use acid. So one of the common form of acid that we will use will be 1 molar of hydrochloric acid, 1 molar, because we all know that 1 molar of HCl, when it is in aqueous form, actually it can dissociate into hydrogen ion and chloride ion, completely, because it is a strong acid. So not only hydrochloric acid can serve this purpose, nitric acid can also serve this purpose. Can we use sulfuric acid? Well, I would say no, because sulfuric acid itself is a dibasic acid, and this dibasic acid, it can dissociate once into hydrogen ion and hydrogen sulfate ion. However, the second dissociation of it, that means the hydrogen sulfate ion can actually further dissociate partially into hydrogen ion and sulfate ion. But this amount of hydrogen ion is not comparable with the original completely ionized hydrogen ion. So even though if we have 0.5 molar of sulfuric acid, it does not look like a good idea to be the solution that we try to use. So we simply cross them out. So by using this hydrogen half cell, we can compare this standard electrode potential of a certain compound. Let's take zinc half cell as one of the reference. So in the left hand side, you can see that we've got an hydrogen standard electrode, and then we have hydrogen gas pumping in, at 1 atm and 298 K. Say for example this time is hydrochloric acid AQ 1 molar, and it is always connected to the voltmeter. This voltmeter is always a high resistance voltmeter, so that because of the high resistance voltmeter, it can give us a more accurate reading. And this hydrogen standard cell is always connected to the voltmeter's negative terminal. On the other hand, we simply place the half cell that we want to measure. This time it is zinc. Okay, we place zinc metal together with a zinc ion in at 1 molar. Say for example zinc sulfate solution. Okay, and then we simply connect it through salt bridge. So by doing this, electron will flow through from one side to the other. Well, definitely we know that zinc will lose electrons more readily, so it will pump electron into the hydrogen half cells. So the hydrogen half cells will undergo an electron accepting process. That means the hydrogen ion will accept the electrons and become hydrogen gas. So eventually hydrogen gas will pump out, and on the other hand, zinc will lose electrons into zinc ion by losing 2 electrons. So that means now this time zinc is actually the electron donating part. That means releasing electrons. So eventually you will notice the potential measured will be a negative value because it is connected to the positive terminal of the voltmeter. Okay, it's in the wrong direction, that's why it's a negative value. So this is the what we call the standard electrode potential of zinc metal. Okay, so by doing similar comparison, okay, we compare with the hydrogen standard electrode, okay, and we can obtain a series of reduction of this potential. Okay, well, this potential sometimes we call it a reduction potential because, as you know that, as you can notice, okay, from the equation, okay, from the table here, they are all talking about a reduction and turn into a negative value. The more negative the value, that means it loses electrons more readily. Okay, more readily. Okay, that means it is a stronger reducing agent. Stronger reducing agent. Okay, so when we look at this table, the more negative is a more stronger reducing agent. On the other hand, okay, when you look at hydrogen, okay, it is the 0 volts. Okay, that means we're treating this one as a standard. The more positive, on the other hand, okay, when you look at this one, okay, like potassium permanganate, okay, it has a positive 1.51. That means the higher the value, the more positive the value, then it should be a stronger oxidizing agent, that it tends to oxidize others. Okay, so by comparing the standard electrode potential with hydrogen standard, okay, then we can know what we call the standard electrode potential. So this standard electrode potential can definitely help us to generate or to formulate the best chemical cell we have in the world. Okay, then definitely the difference, the larger the difference, the higher the voltage. But it doesn't mean that if we use sodium as one of the electrode, okay, and then we compare with the hydrogen peroxide, then this one will give us the best chemical cell. Well, it is right, the voltage is the highest, but it does not mean it's a feasible or workable or controllable environment that we can make a chemical cell. So through this video, hope that you understand what is meant by standard electrode potential and what is meant by a standard hydrogen half cells.